Welcome to Hydromantis webinar. Today we are excited to present to you a new topic, modeling drinking water and process water treatment with GPSX. My name is Rajiv Goyal and I'm the president of Hydromantis, and I'll have the privilege of doing this webinar for you today. I also have my colleague Spencer Snalling sitting remotely, helping with this webinar.
Hello, everyone.
So the items that I would like to share with you today are listed here, and we'll go through some of the introduction items, looking at some of the needs and the challenges and opportunities that we normally are seeing in modeling water treatment plants. I'll also give you an overview of water treatment plant model in GPSX, showing you some of the model components, some of the water chemistry, and the treatment processes that we have built into the GPSX platform for modeling water treatment plant systems. We will not be going through the technical details of each and every model, but it should provide you a good overview of what you can do with the models that exist in GPSX for water treatment plants. Then I'll lead you through a desktop demonstration, and we will kind of some of the things that we will talk early on. It'll become a little bit clearer when we do the desktop demonstrations and show you an example case to show you what you can do exactly. How can you make a layout in GPSX, and what kind of information you need to put in to the models, and what kind of outputs you can expect. I'll follow up with some case studies. So we have planned 3 case studies, one with respect to a drinking water treatment plant that we were working together with a consulting company. Then there are the other 2 that are related to some of the optimization studies that we can do for the process waters in an industrial setup. We'll also have we'll try to, depending on the time, we will try to answer some of the questions that we will get. But in case we are not able to get back to you with the answers to your questions, we will follow it up after the webinar. So let's look into the introduction part. And some of you, I think, in the attendance probably are familiar with the wastewater treatment plant modeling. This is a topic that we have been working for last 30 years, and this is a topic that is very well developed. The wastewater modeling is very well developed just by the fact that there has been a lot of people who have invested a lot of effort and time building the framework of analyzing the processes that we normally find in wastewater treatment plants. So the outcome of this wastewater treatment plant modeling is kind of the simulators that allow you to build block diagram based layouts for any given plant configuration, and then you can analyze those systems with different operating conditions, different inputs, and then try to use this for either plant design or operational optimization or control, basically. So has been quite a mature field, and there are several simulators that you will find in the marketplace, but this is quite limited to the wastewater treatment plant simulations. So when we look at what are the differences between wastewater treatment plant and the water treatment, like what are the differences that makes it a little bit harder to take the same concepts in the water domain, then we can see that the nature of pollutants basically for the wastewater is organic in nature. The concentrations are typically high, and the primary focus in wastewater treatment plant is biological treatment. Not to mention that, well, physicochemical treatments are also important, but the real focus is on the biological side. Some of the process indicators that wastewater engineers are familiar with are the CODs, BODs, TSS. So these are very typical indicators that a process engineer working in a wastewater field is quite familiar with. The treatment technologies are, again, focused mostly on the biological side, and typically you will see activated sludge processes, trickling filters, and MBBR reactors, and several variations of these technologies. But when we look at the water side, the main nature that we know, there is of course some organic pollution in the water sources, but we are mainly dealing with inorganic contaminants most of the time, and their concentrations can change from low to high depending on what is the source. For example, if you have the river water, the inorganic contaminants are much lower in concentration than if you use the seawater for your water supplies. So in which case we talk about very high total dissolved solid concentrations. The typical focus relates to physicochemical treatment. So there is a lot of physical processes we encounter in water treatment systems. And at the same time, there are a lot of chemicals that are being used to remove the pollutants. Our main focus as a water engineer typically relates to the process indicators like TOC, total dissolved solids, TDS, turbidity, alkalinity, hardness, ionic strength, conductivity, and these are kind of some of the variables which are not really as important in the wastewater domain. When we look at the treatment technologies, we are talking about lime softening, ion exchange, RO, filtration, and several other variations that might exist in a water treatment plant systems. I have to admit that there are some biological processes that we also see in the water domain, for example, the biofilters, but the focus largely remains on the physicochemical treatment systems. So where do we stand at present with respect to water treatment plant modeling? So as I mentioned, the block diagram based tools for wastewater treatment plant modelings are very well developed. But when we look at the water treatment plant modeling, the block diagram based tools are not really very well developed. And I don't really know if there is anything out there that is available in the marketplace for people to use and analyze their systems in an organized way. Based on our experience, I think when we look at it, a lot of people's, the water engineers that are out there, they use tedious and time-consuming spreadsheets that have been developed. And the problem with those spreadsheets is that they can still work for individual unit processes, but when you want to analyze different type of process configurations and compare them alongside, then it becomes a very, very tedious and time-consuming exercise. So this lack of systematic way to analyze the water treatment systems, it presents a great problem that we cannot really put so much efforts to actually optimize our water treatment plants. So that was one of the motivations for us to actually look into the side of the water treatment plant modeling and bring out a platform that can actually help people to solve these problems. So if we look at the challenges and opportunities that we can see in this particular field is that the first and foremost, the challenges are that sometimes we have seen working on different projects that there are different sources of water, and the source water qualities could be very different from each other. And the challenge that it presents is that you got to find the right ways to treat the water in different mixes, for example, or when you're shifting your water sources from one source to another, you got to try to make the right adjustment in your water treatment plant. Also, the sources that are there, they could also change in seasonal quality. There could be some seasonal quality variation as well. The third point is basically that whether we are in a process setting or we are in a drinking water setting, in both the settings, we do need strict water quality requirement because drinking water, of course, is a potable source of water and it has great implications on the public health. On the process side, when we are looking at industries trying to treat the water and use it in their processes, they also have definite criteria for achieving those water qualities. Otherwise, they couldn't use that water. So there are several opportunities that we see in this particular field. The first and foremost, of course, is with respect to water conservation. There is a more and more focus that is shifting with respect to water recovery and reuse. And if we want to do that, then in that case, we need to have some adequate tools that we can use to analyze our systems. The other part is, of course, directly related to the cost savings. And we can basically look at, for example, As I said, water treatment plants are more chemical intensive, so more chemicals we add, we can get a better treatment, but it also leads to other problems. For example, a lot of solid generation that might happen if you overfeed your chemicals. So essentially, there is a chance to actually optimize and manage your system in a better way. So essentially, I mean, if we have good tools that we can use on a day-to-day basis, it could allow us to better manage our plants and help us with the cost savings and better management of our systems. The last part that we have here is another segment that is very, very essential, and which is a pretty big segment with respect to the operator training. And this is something we have been doing for the wastewater training simulators, but the point here I wanted to make is that we can also use the water treatment plant simulator to develop simulation-based tools, basically, that can be used for operator training. So better operators will help in the better management of the plants. So those are some of the opportunities that we see in this particular sector. So now, with this introduction, let's go to our GPSX model and try to look at it and see what are the different things that we can do with this particular framework that we have developed for modeling water treatment systems. So first of all, I think first and foremost, I think what we wanted to do while developing this platform was to work with some principal components that are there in the water. So rather than looking at composite parameters of alkalinity, for example, hardness, and so on, we wanted to make the fundamental. We wanted to look at fundamental components that we can then make a mass balance on. And depending on which component, how the components are being removed in each unit process, we could then use basically to develop, our composite or the measured or the observed parameters that are typically used in water treatment plants for management. So just to look at some of the components that we are monitoring, or we can actually model and monitor in the modeling platform. So there are a number of soluble inorganic components that we have, and here is a list. I won't really go through each one of them, but you will find there are most common ones that are there, but you will also find that there are some that are missing. For example, I think we get the questions about arsenic and we get the questions about boron. I think these are the two components we want to add as we go forward. But at present, those two components are not there. But you will see all the manganese, for example, iron, copper, chlorine, and some other common components like calcium and magnesium. They are there for you to kind of input into the model and then track them down as you model as you simulate your system, right? So the other part of it is basically, every water treatment plant system relies on quite a lot of precipitation reactions. So as you add new chemicals, they react with soluble components and create some precipitates. So we are also monitoring those precipitates as its own component, so that when you look at your composite solids that are being produced from the system, you can identify what type of precipitates are there and what is the makeup of those solids. So it kind of helps you to understand, what is the source of this solids that is being coming. Is it part of the chemicals that I'm feeding, or is it part from the input that is coming from the influent itself? So there are a number of them, and it's not a very, it's kind of the most important one that we kind of listed for the water treatment plants, but there could be some others that could be further added into the system. Again, as I said, that even though our main importance is physicochemical treatment in water treatment plant systems, we still do encounter sometimes, for example, if you have ammonia or if you have nitrates coming into your system, then in those situations, you want to do some biofiltration, or you want to utilize some of the biological processes. So to address that, essentially we allow you to have some inputs with respect to the organic carbon coming into the plant, and some of the structure you will see that it is coming a little bit. We have borrowed the structure from how we model it in the wastewater treatment plant. So we have nitrogen components, we have phosphorus component, and some of the organic components. We have tried to kind of limit the number of classes of organic compounds just to keep the complexity of the model limited. Otherwise, but there is nothing prevents us from adding more compounds if there is a need there to model. The other things that, of course, when we are modeling biological systems, then we need to have some bacterial biomass. So we have three types of biomass in this particular model. One is that removes the organic material and oxidize it into CO2 and water. And the other two biomass are ammonia oxidizers and nitrite oxidizers. So, and again, we have some pathogens, 4 types of pathogens in the library that can be tracked throughout the system. So this is kind of a first round of components that we selected in developing our water treatment plant library. Now, as I said, that we wanted to use those components and define the mass balances so that we can track each one of them and we don't lose any mass balances all across the system. But of course, sometimes people are not really interested in each and every individual component, and they are mostly, as a water engineer, we are more interested in some of the other things that we can actually measure in the system. So, for example, pH, different type of alkalinities, different type of hardness, and we can see that total dissolved solids. Ionic strength and osmotic pressure is really important when we are doing RO treatment. So those kind of calculations are built in. Conductivity, resistivity, turbidity, and color. So all these calculations are really important, and depending on what type of water you want to produce, some of these may be more important than the other. We also do calculations for some of the important indices there. For example, Langmuir saturation index and Pecorius scaling index and Risner stability index. These are 3 which are quite common as a water chemistry engineer. If you try to kind of want to figure out what is the value of these 3, basically you can do the calculations, but we track it throughout our system. There are some other components there that we are calculating, for example, activity correction factors, depending on 3 different approaches, and we provide you that information as well. How do we model some of the underlying reactions? So just it's a very, very kind of a high level overview. What are we doing underneath the model? So it's not only the mass balance, but we also try to do some predictive modeling with respect to, for example, if you add certain amount of chemical, what will be the pH of your system? Would there be a precipitation that would happen? So we do all of that underlying chemistry and underlying calculations so that it becomes a little bit of a predictive system, and not only just a mass balance kind of where you put some removal efficiencies and try to estimate mass balances in your system. So what are we doing here? Basically, we are essentially doing ionic speciation for all the compounds that are dissociated in water. So it's like weak acids and weak bases. So all of those basically have temperature dependent dissociation constants in the model, and based on those values we try to identify the ionic speciation in the system. We do very detailed calculation for the pH, so including all the speciation of the ionic species. Then we do algebraic equations, and we have a very robust calculation method to estimate the pH. There is an inorganic precipitation that is modeled with respect to certain precipitates, and we utilize the principles of solubility product and some of the kinetics expressions to make it more dynamic in nature, and that's the way we are estimating inorganic precipitation in our system. Gas liquid transfer. So sometimes, for example, if you have some places where you're stripping CO2 or you're transferring oxygen into the system, we take into account all of those gas liquid transfer processes in this particular model. And again, we have a simplified biological model, so it's not as detailed as the model you would find in a wastewater treatment, but we do have a simple model that can do the biological reactions in the water treatment plant, basically, and take into account, organic removals and nitrogen removals in the system. So with that, just going over some of the unit processes that you can use, and then I will come again to this particular aspect when I give you a demonstration, and probably it will give you a little bit of a better understanding what we mean by this unit processes. But some of the unit processes are essentially the building blocks of a layout. So these are the blocks that you can pick and drop on a drawing board and then construct any type of a layout. Water treatment layout. So here we have broken it down into different tabs, basically. So what you have is a raw water source, and these raw water sources could be different in nature. So we have broken them down into river water, lake water, groundwater, brackish water, seawater, and the difference essentially is not really with respect to what are the components. So they all have the same component, but the components are in different concentration. For example, if you have a brackish water versus seawater, the TDS concentration by default setting is going to be much different. But of course, you can change all these values depending on the specific water that you're dealing with in your system. The other part we talked about is the chemicals, basically, that we normally use in water treatment systems. And you could be using a lot of acids or alkali, different type of nitrogen and phosphorus compounds, or some other water chemicals. So we have different type of dosing unit processes, and there are probably more than 20-30 chemicals that are built into the libraries that you can just dose into your system. So these are basically the chemical feeds that you can include in your layout. The third part is the physical treatment. So in this particular case, essentially, we have different type of, for example, sedimentation tanks. You're looking at sand filters for removing the solids. If you want to remove oxygen from the water, then there are deaerator. If you want to remove carbon dioxide, decarbonation. So there are this kind of physical treatment in which you are not really adding any chemical, but you are utilizing, for example, either the gravity separation, or you are essentially using just the physical means to actually remove or add a certain component into the system. So with respect to the chemical treatment, we have at present we have a neutralization tank, line softening reactor, and some of the ion exchangers that you will find. So there are strong acid and the weak acid kind of ion exchangers that are there. So we have both of them, which are based on weak and strong acids. Strong and the weak resins. And the other component that we have is advanced water treatment, where we have reverse osmosis and an evaporator, where you can basically, try to remove the water, evaporate all the water, and use that for producing pure water, essentially. The other thing is there is a tab for biological treatment, and we don't have as many reactors technologies here as we have in our wastewater treatment systems, but we have the essential technologies like biofilter, I think, is the most common one that is typically used in water treatment plants. So you can use that. On the solid treatment side, so we are, of course, not only concentrating on the liquid side, but we are also managing the solid that are being produced, and we can look at how you manage your solids into the system. So there are essentially dissolved flotation for thickening the solids. There are some settling ponds, and there are some dewatering unit process and the thickening unit processes that we have that can be essentially utilized for handling your solids. So this is not a very complete list, but there are some other things that you will notice when I show you the demonstration. We also have a lot of controllers built into the model, PID controllers, which can be used to control different aspects of your model. But this provides you quite a good overview of what are the components that are there built into GPSX water treatment plant. And just to mention two other processes that are essentially we have listed as utilities, and they are commonly found not in the drinking water systems, but in an industrial setup where you are trying to actually recycle some of the processed water through your cooling towers, and you need to include cooling towers into your water treatment plant systems. So this provides you kind of a good overview of what we have in our model there. Now coming to desktop demonstration, and what I will do is I will try to show you quick demonstration what we have been talking here, and you can see my screen. And so this is essentially GPSX interface, and some of you who might have used it are probably familiar with this. So essentially, when you want to use the water library, there is a process water treatment library there, and we just change the library, and it changes the library to process water treatment library. So it is one platform that can be used for wastewater depending on what models you're using. But in this particular case, we are switching it to process water treatment library. And as you can see that the unit processes that we discussed, they appear on the left-hand side. So we have now river water, lake water, groundwater, and all the other tabs that I was showing you, they are listed here. So you can open up any tab and you can actually look at some of the unit processes that I was talking about. So there is actually a bigger list than I showed you there, but I kind of wanted to just show you the most important ones. That's why I didn't include each and every one that is there in the platform. So essentially, you can have all of this unit processes, and when you want to basically start a layout, what you're going to do is you're going to just drag and drop. So for example, if there is one water source, you're going to just drag it onto the drawing board here, and then you will start building your layout. So in this particular case, just to show you how easy it is to build your layout, you could essentially go to, let's just choose chemical treatment here, lime softening, for example. And in this case, you will place the unit processes, so drag and drop. And with that, you will basically essentially pick up the right modules and you will place it on the drawing board. And the next, you will just connect them together. So here you will have influent that will feed into a lime softener here. And of course, this is not a good layout, as we know that it needs some chemical dosing as well. So what you will do is essentially you will go to the chemical feed and you will then select one of the alkali dosing compound and you will kind of connect it. So this is the way you are going to just essentially build a layout by drag and drop and kind of making the right connections and get to your layout. And once you have done that, then you're going to essentially, we will need some information that we need to feed to the system. And in this particular case, essentially, for example, for a water, of course, we need to define what is the flow that is coming into the system. And GPSX also provides you a very good functionality to actually change your units from any unit you want to work in. So if you want to work with meter cube per day, that's fine. If you want to work with gallons per day or mega gallons per day, all of those units are there for you to choose from. Also, with respect to the composition itself, we have a very detailed characterization of the influent that you will see. And it might be a little bit overwhelming when I open this one, but let's see here. So this is essentially a kind of the information that you will feed into the model. Starting with pH, alkalinity, what is your TSS, TOC, for example, and some of the strong anions and cations that you have in your system, some of the weak acid and bases, dissolved gases, inorganic precipitates. So you will define your wastewater, define your water with the characterization or the properties that you have. And once you have defined it, then what will happen is on the right-hand side, it will do a lot of calculations for you as soon as you enter this information. So here we can see on the right-hand side that some of the water chemistry variables that I was talking about, alkalinity, for example, different type of hardness, different type of stability indexes, ionic strength, for example, conductivity, resistivity, and osmotic pressure. All of this will be calculated for you for the wastewater, for the water. So here you can change anything here and automatically it will kind of calculate the right-hand side. So that is the way you can characterize your influent or the feed water in the most appropriate manner. And once you have done that, then that becomes the feed to the downstream reactors. So that's how you will make your layout. And with respect to the reactors, there are different inputs that you will need. You will also need, for example, some of the volumes. What is the volume of your reactor? What is the depth of your reactor? And some of the kinetics, which probably, if you have some data from the plant, you can actually change the kinetic parameters and trying to, calibrate the model to the observed performance so that you can do your future experimentation with different operating conditions. So you can do all of that. And just to show you the chemicals, we have different feed chemicals here. So you can look at the feed chemical details, and there are different type of chemicals: sodium hydroxide, calcium hydroxide, magnesium hydroxide, NaSCO3, calcium carbonate, and sodium bicarbonate. So this is just the kind of alkali that we have in the system, but acids, there are large number of acids that we have. Also some of the water chemicals. So if we would want to see what is there in the water chemicals, we can look at gypsum, sodium hydrogen sulfide, chlorine, carbon dioxide, ammonia, and some generalized inhibitor that you can use for corrosion inhibition. So there are multiple options to add different type of chemicals in your system. So now, once, of course, I'm not going to make a full layout here, but what we are going to do is we are going to use a layout that I already have. And let's just use the layout so that I can show you what to expect once you have made the layout. So this is a layout, and this is a typical lime softening layout that you will find in water treatment systems. There is a lime softening here. You are adding lime to the system. You're removing, sometimes they are together. So this is called clarity flocculator, or sometimes they are just together as one unit, but in GPSX you can model them as two. One is a reactive unit, the other one is a settler unit, sedimentation unit. So you can model them together. The water that comes out, it goes to recarbonation, where you are adding carbon dioxide to increase the pH of the system. Sorry, to reduce the pH of the system. And after that, going to the sand filtration, chlorination, and the clear water storage, and ultimately to the distribution. On the other side, we can look at all the solids that are being generated here. So you can look at the solids that will be settling here. You can try to use a thickener or the sedimentation tank to further thicken these solids, and then maybe use dewatering and use it for solid disposal. So essentially, you can build any type of layout using these principal components that we have on the left-hand side. So once you have made this layout, the next point is, of course, what can we do with this? So we can go to simulation mode. And as you can see that GPSX has a very well laid out simulation mode, where we can conduct various type of analysis. So in this particular case, we have certain controllers that we have where we can control how much water we want to feed, and how much chemicals we want to feed, how much CO2 we want to feed. So we can control this one here from the sliders if we want to. In this particular case right now, we are not feeding any chemicals, so there is no lime, there is no CO2. And if I just run the model just like that, essentially, for a day, and just to mention here that we still keep the dynamic part of the GPSX to model your system in a dynamic way, so that when you make changes, you run a known transient system and you have different dosing at different times, you can model those kind of behavior into the system. So once you run the model, you can see there are a lot of outputs on the right-hand side. So you can see, of course, there's a flow of meter cube per day. There are some TSS components and different observable or measurable components, or the variables that you will see for the water chemistry. They are being generated for you here. So we can see that this water has a total hardness of 373. with some alkalinity there. There is a non-carbonate hardness, which is 172. And there is a pH, which is 7, and not too much of TSS, and very little DOC there. So that's kind of the source of the water. And when we look at different treatments, since we are not adding any lime, we don't expect any reaction to happen. So we can see that whatever is coming in, that is the same thing going out, basically. So there is nothing happening, it's just flowing through. And similarly, we can look at many different parts of the system, even our sludge, basically, because we are not adding any chemical. We can look at our sludge, and we are not producing anything. We are only producing 200 grams, which is probably the removal of the TSS that is coming in. It's a very small amount of solids. So now what we can do is we can analyze different scenarios. For example, if I start to do a lime dosing, what will happen is there is a flow of 200 liters per day for lime. And when I run the system now, we will see that there will be some hardness that will be removed. There will be some calcium carbonate that will be generated, which will be sedimented into this clarifier and removed through the solid sides here. So we can see also the dynamics, as I said. So you can see that the pH right now, since we are only adding lime, is pretty high. It's about 10.56. And our hardness has come down, basically. So hardness is now 214. So we can look at that at the lime softening as well here. And if I show you what's going on with the hardness, we started with 368 here. And after adding 200 liters per day of calcium hydroxide, we can get down to 214. And we cannot go below this because there is a known carbonate hardness which cannot be removed by adding lime. So that's why this is probably the bottom line that we can achieve. So even if we add more chemical, it's not going to be helpful. It's only going to generate more solids. So here, if we look at how much solids I'm generating, I can look at, okay, now I have 225 kilogram per day of solids that I need to deal with, right? And again, if we look at the treated water, we can see that our water pH is pretty high right now because we are adding lime, but we are not adding any carbon dioxide. So we are not doing any recarbonation. So now if I were to go and try to do lime dosing with CO2 addition, in which case I'm adding 100 meter cube per day of CO2, then I can run my simulation again and look at what will happen to my effluent water here. So in this case, we can see that my water is going to around 6.9 basically, and we are adding 100 liters per day, and we are doing softening, so we are also coming down with respect to our hardness basically, and it has gone up a little bit because when we add some more here, it's going to create some additional precipitation that is not being removed from the clarifier. So you can analyze the system in a very, in a very systematic way and try to look at what is the issue, what is happening at each and every point, basically, because it produces a lot of information for you, not only at the influent and effluent, but also at every connection point in the treatment plant. So sometimes it is very difficult to get all this data from the plant because you can't really take all the samples and analyze them. So this is probably the best way to get an idea about what is a quality that you have at a given point in your system. So so you can do all of those kind of simulations using this particular tool. So that's kind of, I mean, there are many other features here. One is, of course, a feature of Sankey diagram. You can easily draw diagrams like, you can look at how my water is flowing throughout the system. You can do that. So it is very good to visualize the mass balances of the flows, mass balances of all the contaminants that you have. And it provides a very visual observations, and you can easily see if you made any mistakes in setting up your model. The other part is, of course, the mass balance tables, and you can also create a lot of mass balance tables. And this probably might seem a little crowded, but you can actually, some of the things you can just remove, the things that are not required. and you can then rearrange these at the right point of the place. So it provides you kind of a very easy way to prepare your mass balance diagrams as well. So with that, I think I will just move on to our next topic that was showing you some case studies. And one of the case studies that I wanted to show you here is with respect to a water treatment plant model that we worked together with a consulting company. And one of the main objective of this particular exercise was to determine the best configuration, treatment configuration, so that we can treat the water that is coming from 3 different sources here. So, the problem in this particular case was that the makeup of the water was different. So one source had high TOC and TSS and low hardness, but the other one had a high hardness, low TOC and TSS. So there was quite a bit of a discussion on what is the best configuration and how do we optimize the system so that we can make sure that when we are treating different mixes of these waters, we are able to do that with a given plant configuration. So the main objective of this one was to find the best configuration and at the same time try to achieve some of the targets with respect to hardness, TOC, turbidity, pH, and alkalinity, and while minimizing the operating cost. So operating cost was one of the key consideration, that we don't want to add too many chemicals and we want to essentially have, keep the cost at the lowest. So that was the principal consideration in this particular exercise. So before doing the modeling or before, after setting up the model, of course, the first and foremost consideration was how well we are predicting with the model. So we compared the model outputs with some of the jar testing data that was available in some of the reports. And we compared that by setting up a simple model in GPSX and then trying to model the pH, alkalinity, TOC, and hardness, which are some of the typical things that we wanted to which was some of the target criteria. So this is the information that was collected from a jar test data. And when we run the jar test, according to the conditions that was there in the jar test, we could see that there was a very good relationship between the predicted values versus the values that were measured in the jar testing thing. So this is one of the important exercise when you want to use it and validate it. Basically, you can do some cross checking of the model outputs with some of the data that you might have. So this was one of the things that was done. And then, of course, what we did was we ran various type of configurations with different type of mixes and try to produce a lot of information with respect to what's going on at every point in the treatment plant. So this is some of the tables that we could produce with respect to some of the important criterias, and look at every different sections of every stream of the plant and try to see how we are doing at every sections and whether we are trying to achieve the performance criteria or not. And while doing that, we were also producing all the costs. So once the cost models are set up, so we are already estimating how much chemicals are going to be needed. And once we add the chemical cost, then we can estimate how much is the chemical cost that will be required for a specific configuration that we are analyzing. So not only the chemical, but again, the solid production is one of the important considerations. So we can definitely keep on adding a lot of chemicals, but the side effect of that is, of course, producing a lot of solids. So, and that, of course, can be a very, very big component in the operating cost. So that was combined together with the chemical cost. That was one of the criteria to kind of assess what is the best configuration. Then we ran many simulations, and based on those simulations, we tried to come to an optimized plant configuration that was satisfactory and also led to reduction in the operating cost compared to the initial configuration that was suggested. So that was kind of a pretty nice and interesting exercise and the validation of the models. And a very practical way to use the models, essentially. And again, like I said, the Sankey diagrams were very helpful to look at how we are distributing the things, whether we have set it up correctly or not. So it was very nice to see it in a very big model, because once the models get very big, it becomes very difficult to see whether they are even set up correctly or not. Again, the mass balance tables, of course, were very helpful to just look at the information at different sections and make sure that things are in the right order. The second exercise that I want to show here is that with respect to a case where there is a water treatment plant which is being used to produce a water that can be used as a makeup water for cooling tower. So some of you who are from drinking water and probably are not familiar with cooling tower, the cooling tower are kind of principal components, or they are one of the important components in any process water treatment systems, basically, and quite a lot of them use a large amount of water, because just for the cooling of the water itself, they need a lot of water. And there is a huge demand, and any water that can be saved in the cooling towers could be basically a source of revenue for industries. So in this particular case, the makeup water, of course, is required, and the quality of the makeup water is really important. So depending on the quality of the makeup water, it really becomes how much water actually you will need. So more contaminated water you have, the more quantity you will need. So more pure water you have, the less water you will need. So essentially, one of the exercises in this one was to determine the amount of water that we will need under given conditions of treatment, and under given conditions of recirculation water that was required, and some of the evaporation losses and the drift losses that are going to happen in this cooling tower. So essentially, the purpose was to look at what happens if we add lime, for example, and soften the water, and that softened water will then reduce the makeup water demand and reduce the chemical demands as well, and system overall the cost of the system could be reduced. So it was more like a sensitivity analysis, where you would like to see essentially how the lime dosing is affecting the rest of the system here. So in this particular case, we also used a PID controller to keep all the analysis in the same, keeping the same basically with respect to the TDS, or the total dissolved solids that were there in the recirculation water. So a controller was used to control the amount of makeup water calculation, so that the TDS in the recirculation water is at a set point that we wanted to keep. So just the output of this one, and quickly going through this, we looked at increasing the lime dosing, and when we increase the lime dosing, of course, the pH in the system goes up and our hardness starts to go down. But the side effect, as we know, is the solids that starts to keep on going up, and of course our makeup water requirement starts to go down. So here you can see that from almost like a 5,200 to 4,000, which is a 30% reduction in the water demand for makeup water if we kind of do the lime treatment. At the same time, there are some other chlorine requirement and the acid requirements in cooling towers are also seen to be going down as we do the lime treatment. So if we look at it, basically we can see that as we keep on increasing, we come to a point where we are at a minimum. But if we start to add more, then essentially our system performance is going to go down. So essentially there is an optimum point where lime softening can give us the biggest benefit with respect to all of this thing combined. So, but if we overfeed, then of course the softening performance first of all goes down, and then our solid production goes up, makeup water requirement goes up, and chemical consumption goes up. So it's a very useful exercise to understand your system in a very significant detail. The third exercise, of course, there are, I think, quite a number of you who are probably interested in RO systems. And this is a little bit of a hypothetical exercise that we try to put together just to show the capability of model that you can use in GPSX to analyze the system. So this is a two-pass, two-stage system. and we have a feed, and in this particular case we wanted to see how the feed pressure in each of these modules is affecting the water recovery, overall water recovery of the system. So in this case, we set up the model, and just to go through some of the typical inputs that we have, we can look at some of the, you need to set it up with respect to number of vessels, the membrane area, and some of the other properties of the membrane unit here, and followed by some of the membrane property itself with respect to, for example, mass transfer coefficient of the water and mass transfer coefficient of the solute. So you can set up those things. They are membrane specific. And once you set this up, then we can estimate what is a rejection and what is a water recovery. Also, some of the feed operating conditions, basically, so they were set up, initial conditions. And once after that, basically, we can run the model and see how the system is going to behave. And we can look at the feed, and we can look at the treated water and the brine concentrations and how they partition when you're trying to run the system. So these are some of the important parameters that you can actually very easily determine by the model. So once we run the model and we use an optimizer, built-in optimizer in GPSX, try to optimize the recovery. And when we want to increase the recovery from 49% to 60%, then the pressures at each stage, basically, the optimized pressure comes out to be, it shows the initial pressure and the optimized pressure, and shows some of the changes that we need to make if we want to get to this particular recovery. And of course, when we increase the recovery, then the side effect of that is that there is a scaling potential starts to increase because your brine starts to get more concentrated. So the GPSX model also has some built-in feature in the RO unit process where we can find out what is the percentage saturation of over the solubility product for some of the common scaling scales that can form, and it can provide you guidance with respect to whether increasing the recovery might lead to some scaling potential, and do you need to add some acid, for example, or do you need to add some scale inhibitors there. So there are a lot of things you can do with that. So now I'm coming to just the end of our slideshow here, and I just wanted to mention as a side note here, because as I said early on that there's a lot of demand, or a lot of people out there who want to do the water treatment plant training. And this has been very successful, actually. We have seen a great success with respect to the wastewater treatment plants training simulators for training operators. And in a similar vein, basically what we can do is we can actually try to build a model, GPSX model of a plant, and then we can create this kind of operator training simulators, basically with a nice graphical user interface, where you are not bothered with too many complexities of the model. You are only shown some of the details with respect to the inputs that you can do, for example, the chemical feeds, some of the pumping flows and stuff like that. And then you can just run the model and you can see how the system is going to behave. So this is working out to be a great tool, especially as per our experience in the wastewater. And actually this particular simulator was also used for doing training in one of the conferences in British Columbia, and we used this simulator to train some of the operators, and the feedback was really great. So this is another opportunity for building either custom or out of the box simulators, basically for training operators in a very immersive environment. So this is different than PowerPoints. This is different than all the pen and paper kind of slideshow type of trainings. This is very, very immersive, very interesting for operators to basically make the changes and see how they're going to behave. And finally, just to wrap it up, basically just wanted to give you a little bit of a sense about that. We have had a pretty good success using this platform with one of our clients, who was actually the impetus for us to develop this platform. And since its development, they have used it for their facility, which is a very, very complex water treatment plant. And they try to model it and try to use it to understand the system and try to figure out what are the opportunities that they have with respect to the chemical feedings that they are doing at different stages. So, which means that essentially, as it is very clear from their code, is that it is one of the very good tools actually to give you a lot of power to analyze your system in a very systematic way. So with that, I think I would just like to wind up. I know that I've gone over my time, but I would just summarize it. We have now a block diagram based tool for water treatment plant modeling in GPSX simulator. We have had it for some time, but we released it recently in version 8. So you can use it for various purposes, as I showed you in my slideshow. But first and foremost, you can use it for making the water balances. Basically, you can do it for solid balances, water balances, analyzing water quality, also looking at precipitation type of things, the tool, as I showed you with some examples, could be a very powerful tool actually to look at some of the optimization that you can do in the water sector with respect to the chemicals, with respect to the solid productions. And last but not the least, I think, is the fact that once you have a model, you can also actually do a customized simulator for the operators, not only for training, but also for day-to-day, basically just learning or even trying to figure out what-if scenarios, analyze what-if scenarios. What will happen if I do this? What will happen if I do this? So those are some of the I think things that we are really looking forward to going forward, and I hope that many of you will find it interesting and useful for your own applications. With that, I would like to wind up and thank you very much for your attention and listening to us.